I would like to give a presentation on 1D and 2D hydraulic model coupling integrating. There are some software which does 1D main channel and 2D floodplain coupling. In my opinion and based on my study here, I would like to show you that the 1D 2D model coupling is a wrong method. It is tedious, time consuming, and it gives inaccurate result. When you are developing a 2D model, it should be completely 2D model. It is easier, faster, and more accurate. Here is a comparison of a 1D and 2D model grid plan view. If you have a 1D model like Hackgrass or Mike 11, usually models have spacing cross section about 50 to 100 meter interval. For 1D model simulates flow field in the main channel and floodplain. Compared to the 1D model, 2D model has small size grid. Each grid has nodes and each node has velocity in x and y direction. The 2D model also simulates water surface elevation at the center of the grid. So if you compare 1D and 2D from the grid, you can see the difference of accuracy. Here is the governing equations used by 2D model, 2D Stern-Wiener equations. The 2D model uses a two-dimensional continuity equation, equation number 1, and equation number 2 is momentum equation in x direction. Equation number 3 is momentum equation in y direction. So momentum equation in the model is solved in x direction, velocity flux u and goes to continuity equation. And momentum equation 3, velocity flux v is solved and goes to continuity equation, and then continuity equation solves the water surface elevation. The 2D model also uses two-dimensional bed shear stress, depth average turbulent shear stress, and dispersion. Here is an example how 2D model simulates or calculates velocity, magnitude, and direction. In 3 out of the 3 nodes, node number 1 has velocity in u and v. Based on its magnitudes, we get the resultant vectors. In node 2, similarly, based on magnitude of u and v, we get the directions based on the vector. Similarly, for node 3, based on the magnitude u and v, we get the direction. This slide shows an example of 1D governing equations for hydraulic modeling. As you can see, the continuity equation doesn't have the velocity flux in y direction, and it doesn't use the momentum equation in y direction. At the same time, 1D hydraulic model does not use eddy viscosity and turbulence. But in reality, when flow in river crosses hydraulic structure like a breeze culvert, at the same time in floodplain flowing obstruction building and variation in roughness, there is a turbulence and there is a multi-dimensional flow. So if you are applying a one-dimensional model, it is simplified method compared to 2D model. There is misconception about 2D model that 2D model doesn't do 1D flow field. But the reality is that the 2D model can simulate both 1D and 2D flow fields. Here is an example. You can see when the flow in the main channel, the flow is parallel to the banks, and that means it's one dimensional. However, it's close to floodplain, and if you have an obstruction, it can simulate two-dimensional as well. So 2D model can simulate both 1D and 2D flow fields. An expert hydraulic modeler knows that there are two types of boundary conditions. One is open boundary, second one is closed boundary. Open boundaries are upstream and downstream boundary conditions, and closed boundaries are side walls. There shouldn't be any artificial forcing inside the model. If you are coupling 1D main channel with the 2D floodplain, that is artificial forcing inside the model. In next few slides, I would like to show that the coupling between 1D and 2D models is a flawed method. I developed 1D Hackgrass model and a two-dimensional SMS SRS 2D model. Hackgrass model has the 20-meter interval of 1D cross section, whereas the SMS SRS 2D model had a 20 to 30 centimeter grid size for the 2D model. As you can see here, the cross sections and the model developed for a natural channel with a ripple pull sequence. If I'm using 1D hackers, I might be missing some of the flow field in the ripple or pull. This is a flow trace animation of flow fields simulated by 2D model of the natural channel. This channel has a ripple pull sequence. As you can see, flow here is definitely two-dimensional. If I'm applying one-dimensional model, that model cannot accurately simulate this flow field. Now I would like to compare velocity magnitude simulated by 1D HACRAS and 2D SRS 2D model. This slide shows the longitudinal distribution of velocity magnitude. As you can see here, the HACRAS simulated flow field in many locations are not matching with the two-dimensional velocity magnitude. Now in terms of direction, if I am coupling between 1D and 2D model, I take the direction from the 1D cross section and apply it for the 2D flat plane. So if you can see here in many locations, direction of 1D cross section is not matching with the two-dimensional flow field. When flow overtops the bank and goes to flat plane, there might create reverse flow or circulation. A 2D model can simulate this reverse flow or circulation. However, if you are applying the one-dimensional model, that model cannot simulate this reverse flow. There is one argument for coupling 1D and 2D hydraulic model, that is missing of channel bathymetry or geometry data. If you have channel cross-section data, you can interpolate the data to create the missing bathymetry geometry data, and you can combine the interpolated data with the flat plane topographic data and create a completely 2D model. When you develop hydraulic model, use either 1D or 2D, but not coupling between 1D and 2D. If you have cross-section data and you don't have the channel geometry data, you can interpolate the channel geometry from the cross-section data. 1D model should be completely 1D, but it will be less accurate. 1D 2D coupling is complex, tedious, and time-consuming. 1D 2D coupling has no benefit, but instability and potential inaccuracy. 2D model should be completely 2D. It is easier, faster, and more accurate.